Hello guys, and welcome to the first lecture of the course Introduction to Classical Mechanics. I'm Rashid Hamdan. This course is designed for non-physics students, so it's going to be on the beginner level. I'm going to try to cover in it material from motion, Newton's law, work and energy, and others. Our first lecture in this course is called Physical Quantities and Measurements. So let's start. The first question we're going to ask is, what is physics? Physics is one of the most fundamental scientific disciplines, and the job of a physicist is to understand how the universe and everything inside the universe behaves. If we look up the literal meaning of the word physics, it means knowledge of nature. So in physics, we're going to study matter that is found in the universe, and we're going to see how it behaves or moves throughout space and time. From the tiniest particles like protons and electrons inside the atom to, for example, planets going around the sun, or to even much bigger stars and galaxies. All these are under the big discipline that is called physics. Physics has to be based on observation and measurement. Since it's the study of nature, it has to be based on the measurement of nature. So anything that we claim to be a law of physics has to be verified by measurement or by observation. However, as scientists, we need to understand that any kind of measurement we have has its limitations, it has limits. And understanding these limitations is very important for us as scientists. We have to understand how these limitations affect the theories that we have. We have to know where we can apply these theories and where we cannot apply them. Of course, the more precise our measurements and observation are getting with technology, the more accurate our understanding of nature becomes. So by better measurements, we have better understanding, we have better theories, and then we can predict better what's going to happen in nature. Now, since physics is based on measurement, we have to know what are the things that we can measure. The things that we can measure or we can quantify either by direct or indirect measurement, these are called the physical quantities of nature. For example, if we take the mass of certain number of apples, mass is a physical quantity. We can measure mass. If we run a marathon, the time it takes us to run a marathon is a physical quantity. We can measure time using a stopwatch or something else. If we look at the volume of water inside a tank, that's a physical quantity. We can measure it. Again, we can either do a direct measurement or an indirect measurement. So now our job as physicists is to understand these physical quantities and find the relations between these physical quantities and see how these quantities evolve in different situations. By doing that, we got what we call the physics laws. And these help us predict how a certain situation or a system, a certain physical system, is going to evolve from initial conditions to later conditions. And that's what all our technology and modern industrial revolution is based on. Now we can make prediction of each system, of how it's going to behave, so we know the outcome of the system beforehand. Now, when we look at physical quantities, they are divided into fundamental and derived quantities. Fundamental quantities are the quantities that don't depend on other quantities. They only depend on themselves and cannot be derived or defined in terms of other quantities. In physics, there are actually 7 fundamental quantities. We're going to focus on 3 of them: length, mass, and time. Those are what matters for us in mechanics. But these quantities, if we look at these quantities, they are only defined in terms of themselves. If we look at the length, how can I define length? I can only define it as the distance between 2 points. So that's basically the same as mass and time. I can measure them, but they are based on themselves. However, other quantities in physics, that we have a lot of quantities, are all derived quantities. So basically they are defined in terms of the fundamental quantities, and we can derive them from the fundamental quantities. Example, volume, force, kinetic energy, pressure, all these are derived quantities. They can be defined in terms of these three: length, mass, and time. Now, whenever we do a measurement, we have to have a unit. So to understand measurements, we need to understand what a unit is. A unit basically is a defined magnitude of a certain quantity. So it's a set magnitude of the quantity itself that we use to measure other quantities of the same kind. So if we were measuring mass, we agree together what a kilogram is. There's agreement between scientists what is 1 kilogram, and then we measure everything relative to the kilogram. So we can measure things as 10 kilograms, 1.5 kilograms, million kilograms. So we are relating them to a known quantity. Of course, we have different quantities that, different units that measure the same quantity. So the physical quantity itself cannot depend and does not depend on the unit we use to express it in. So we can express the same physical quantity in different units, and it shouldn't matter for us. But choosing the right unit, depending on the situation we have, make understanding the situation much easier. For example, if we look at the period of rotation of the Earth around the Sun, the time it takes the Earth to go one rotation around the Sun, we can express it, that's time, right? So we can express it in hours, that's 8,766 hours. That doesn't really, we cannot relate much to that number. We know it's a lot of hours, and is that it's hard to relate to it. So instead we can express it in a more agreeable unit. So we can express it in days. In days, that the same quantity, it's 365.25 days. So it's more relatable now to us. Also, we can express it in years. Time to go around the sun is 1 year. And basically that's the definition of the unit, right? 1 year. However, if we look at a different quantity, like time still, but we are going, the time it takes us to go from home to a store. It doesn't make sense to express that in days or years. Instead, we can either express it in hours or in minutes. Now, in science, there is something we call the International System of Units. It's abbreviated as SI, and this is based on the metric system. So the scientists got together and they agreed on using a certain unit for all the fundamental quantities. So each fundamental quantity now have a base unit, and we use that to express that quantity. The quantities we care about, length, mass, and time, are expressed in meter, kilogram, and second. And of course, the abbreviation of meter is M, the abbreviation of kilogram is kg, and that for second is S. Now, the derived quantities don't have base units. Their units are derived from the units of the fundamental quantities. So for example, force, the SI unit of force is Newton. And that's based on the SI unit of the fundamental quantities. So 1 Newton is just 1 kilogram meter per second squared. The unit, for example, for pressure is watt, and 1 watt is 1 kilogram meter squared per second squared. So the quantity is derived from the fundamental quantities, and its SI unit is derived from the SI unit of the fundamental quantity. One more thing before we go into starting with our physics course is a little bit of mathematics, what we call the scientific notation. We usually express things in a decimal form, but because quantities differ widely, and sometimes we need to compare different quantities, it's not always preferable to write them in the decimal form, because the quantities might be too big or too small to see to make the comparison properly. So instead we use the scientific notation. So in the scientific notation, we highlight the significance of the value, and then we can compare them easily. So we can write each number in this form as m times 10 power n. N is called the significant, and it is a number just between 1 and 10. So only keep one digit before the decimal. And then we put the 10 power n here, and n is the exponent, and we it could be positive or negative. Of course, it's an integer, positive or negative integer. Let's look at an example how that works. If we're trying to compare three distances, the radius of the Earth, the radius of the Moon, and the radius of a hydrogen atom. If we express them in decimal form, we got 6,003,700 meters, 1,700,000 meters, and the hydrogen atom 0.000 something. So it's very hard to compare them in this decimal form. Instead, if we write them in the scientific form, the radius of the Earth is going to be 6.37 times 10 power 6 meter, and that of the Moon is 1.7 times 10 power 6. So first thing we do is we compare the exponent. And it is the same exponent, so they have the same order of magnitude. So then we know that the Earth and the Moon radiuses are comparable. Of course, the Earth radius is around 5 times larger still, but they are comparable. However, if we look at the radius of the hydrogen atom, the exponent is 10 power minus 10. So we don't have to look at the number here anymore. We just compare the exponents. We know it's 10 power 16 times smaller than the radius of the Moon or the radius of the Earth. So this makes the comparison between numbers much more easier, and we can understand the numbers or the values of the quantity better. Now, one more thing we want to talk about is the unit conversion. Since we know that the same physical quantity could be expressed in different units, we need a procedure to convert from one unit system to another unit system. Especially that in different science disciplines, they still prefer to use different units. So in chemistry, for example, they use the CGS system, which is based on centimeter, gram, second, instead of meter, kilogram, seconds. And in astronomy, it doesn't make any sense to measure distances between stars in meter or in kilometer. Instead, we use the light year to measure that. So we need a procedure to convert from one unit system to the other. Let's look at an example. If we have a pot of gold, and we are given that the density of gold is 19.3 gram per centimeter cube. That's the CGS system, it's gram, centimeter. So how we convert this to the SI unit of density? Before we get to the conversion, let's look at what does the unit itself tell us about the quantity and the meaning of the quantity. If we look at the unit of density, it's gram per centimeter cube. Gram is the unit of mass. Centimeter is the unit of length. So centimeter cube is length cube, so it's volume. So we know that density is mass over volume. And the meaning of density, it's the mass of one unit of volume. Or if we have 1 centimeter cube of gold, their mass is going to be 19.3 grams. So from the unit, we can understand the meaning of the derived quantity itself. So let's get to the conversion. The SI unit of mass is kilogram. So we need to convert the gram to kilogram, and we know that each gram is 10 power 3 kilograms. For length, we have meter, and 1 centimeter is 10 power minus 2 meters. But we don't have centimeter here, we have centimeter cube. So we have to cube both sides, and we got 10 power minus 2 cube, that's 10 power minus 6 meter cube. So what is the procedure of the converting of the unit? So I first start by writing the unit as a ratio. So I have 19.3 gram over 1 centimeter cube. And that's what we said is the meaning of density. So now I replace the units in the numerator and in the denominator. In the numerator, I replace gram by 10 power minus 3 kilogram. In the denominator, I replace centimeter cube by 10 power minus 6 meter cube. Then I keep the unit as it is, and then I group the other digits. So I got 19.3 times 10 power 3 kilogram per meter cube. In decimal form, I can write this as 19,300 kilogram per meter cube. Or each 1 meter cube of gold has a mass of 19,300 kilogram. Now, of course, we can write this in the scientific notations that we talked about. And in the scientific notation, we write it as 1.93 times 10 power 4 kilogram per meter cube. You have to think about units and notation, scientific or decimal, as a little bit different languages that we use to express the same idea. So it doesn't depend on the language we use as long as we understand what we're talking about. So you have to use the same language that others use, but it doesn't mean that it's the only right language to use. So we might switch from decimal to scientific notation depending on which is easier to understand. Same as units, we might express in SI unit or in other unit system. Thank you for watching the first lecture, and if you have any questions, please write them down in the comments, and I will see you in the next lecture. Thank you.